colleagues, students, ladies and gentlemen, friends, welcome to the fall semester Ørsted lecture 2016. I stand here where our rector, Anders Bjarklev, should have stood, but he's now standing on an entirely different continent, actually. He's traveling these days in the US. So I get to substitute for Anders, and that's a great privilege to me. You don't need to be famous and to have a track record of collaborating with people from DTU in order to be invited to give an Ørsted lecture. You just need to be famous. However, in this case, with Frank Bates, both things are true. Frank Bates is indeed famous, and he has also collaborated with people at DTU. Actually, he had collaborated with people, and also he has touched the careers of people at DTU, especially my own, and also people here in the room. Christopher Almdal brought Frank Bates to the attention of the Ørsted committee in order to consider him if he would scale out on the golden weight to be eligible for such an invitation. And indeed, I think he scaled out all right. And Viggo Tvergaard will talk to us about this in a moment. Now, I was a postdoc with Frank Bates back in the last century, the last millennium actually. It's a long time ago, but so that's my history. And coming to Minnesota, that's how it's pronounced, not Minnesota, it's Minnesota, of course changed my career and the options that I had later on. So in one way, I could be grateful to Frank for actually standing here, substituting for our president. And in a way I am, even though this has got nothing to do with polymers, apart from this microphone maybe, or neutrons, apart from the glorious future of the European spallation source, which is being built just very few kilometers from here. So I am especially happy to stand here and welcome and open this Ørsted lecture and welcome Frank. During lunch, Frank, he asked me to do this short, and I told him I would do it short and personal. And the most personal, short introduction I can give to Frank is that Frank and I, we actually use the same brand in men's underwear. Is that short enough for you, Frank?
Thank you.
Is it personal enough, do you think?
Thank you.
Now, how do I know that? Well, everything begins and ends with neutron scattering. And so does this piece of information, because I've been with Frank to NIST in Washington to do neutron scattering. And when you do neutron scattering, you focus on the job. And then, of course, sometimes you have to sleep. Sometimes you have to eat. Sometimes you even have to change your trousers, but that's not the focus. And that's how I know that we use fruit of the loom. Is that still it?
Yes, sir.
Okay. So that makes me even more happy. A neutron, Frank Bates, and fruit of the loom can bring us all together, and I can introduce Frank in this way. So I hope you'll have a very interesting lecture. I can already now make the sad announcement that there will be no neutrons in this lecture, even though I'd hoped for it, because neutrons and the history of Frank and Denmark is very much an intertwined story. Started with DR3 at Risø. And of course now we have got the European spallation source coming up, not exactly at Risø, but definitely something that will be used for material science and especially scattering of polymer blends and the sort. So all the best of luck to Frank in his lecture, and now Viggo will tell you some more hard and maybe serious facts.
Well, I'll do it short, as you like, Frank. And I think enough has been said about, and everybody understands that you are famous. I would like to mention that when we looked at you, as suggested by Christopher, we of course noticed immediately that your publication record is very impressive. Close to 500 articles you have published. You have, according to the Web of Science, an H index of 96, I found. And one of your papers is cited more than 2,500 times. Other papers cited more than 1,000 times, all very impressive. And I would like to mention that as a recognition of this, Frank was in 2002 elected as a member of the very prestigious National Academy of Engineering, and he has also later been elected in 2010 for the American Academy of Arts and Sciences. All very prestigious. Please do take over and give your lecture.
Thank you very much. Well, it's truly a great privilege for me to be the Ørsted lecturer. Spent many a great weeks, even months in Denmark, and have had the opportunity to work with some of your great scientists and engineers. I want to thank, to start with, the Executive Committee for the invitation. It's kind of like coming home for me, and I'd like to begin the lecture by giving you a little interesting piece of information about your famous scientist Ørsted. The American Academy of Arts and Sciences, which had its induction ceremony last Sunday, and I was happy to be there to help induct one of my colleagues. It was started in 1780. This is the oldest academy in the United States. You'll recognize a few of the names of the Americans who are in the academy. And I'll also point out that they bring in foreign associates. Jean d'Alembert, a well-known mathematician, and Leonard Euler were in the first elected class in 1781. And in 1849, the namesake of this lecture and the founder of this institution was elected to the American Academy of Arts and Science. The reason I know there's something special is I wrote the Academy when I was asked to give this lecture and asked for a copy of the acceptance letter, which you're required to send. They have George Washington's, Ben Franklin's, d'Alembert's, and Euler's, and they went in the archives and discovered to their dismay that Ørsted never sent an acceptance letter. So I'm here to report to the administrators of the institution that one is wanting, and Martin, if you attend to that, my colleagues in the Academy would be very happy. With that little piece of information, I'd like to move on to my talk. I'm going to tell you about a story that's unfolded in the last few years about quasicrystals and quasicrystal approximants, and I'm going to try to connect what happens in self-assembling soft materials to what happens in metals and alloys. I've had great colleagues to work with me on this project. Sang-Woo Lee, who's a professor at RPI now, Tim Gillard just graduated a few months ago, went to 3M, and Chris Layton is my colleague in the department who was trained in superconductivity and magnetism, and you'll see the insights that he's helped bring to this program as I go on. I'll start by showing you a picture that Roger Penrose published in the 1970s, although I think this pattern was probably discovered back 1,000 years ago, probably in the Arab world. Roger Penrose discovered that you could develop aperiodic tiling patterns based on rhombi, just two rhombi, but never a single five-fold symmetric element, that tile space with very magical relationship between the aspect ratio of the rhombi governed by the golden ratio. So there's a beautiful connection to the underlying number theory and mathematics associated with basic mathematics that is played out in these now familiar tiling patterns. This does not have translational symmetry, but it has orientational or aperiodic symmetry. And what I'd like to do is to highlight that in 1984, Danny Sheckman discovered, while peering into his electron microscope, a 10-fold symmetric diffraction pattern that appeared to violate the rules established in the 1800s regarding periodicity in nature. And this discovery then spawned the development of many different alloys, metal alloys, multi-component alloys. I show one example here that can actually be grown into macroscopic crystals with the seemingly forbidden five-fold symmetry, icosahedral symmetry in this case. I want to answer the question, hope to shed light on the question, why do quasicrystals form? That was not answered, although Danny Shechtman did win the Nobel Prize in 2011 for this fantastic discovery, which changed the way we look at condensed matter. And I'd like to ask the question, are these equilibrium or metastable states? And I'm probably not going to make a definitive answer to either of these questions, but I'd like to shed light on it. And these are results that have come about in the last couple of years. To do that, I'm going to start by focusing on the class of materials that I spent a lot of time in my career studying, block polymers. A block polymer is a material that's made from long sequences of one kind of repeat unit, here blue, connected to a second kind of repeat unit, here shown in red. These are flexible chains that can coil up into Gaussian or random walk coils, and the properties, the thermodynamic self-assembling properties, are governed by three very simple parameters. The degree of polymerization, the entropy of the system is inversely proportional to the length of the molecules. The enthalpy of mixing is determined by a segment-segment interaction parameter. That's an interaction energy. And the composition of the molecule, that's the size of the red block versus the overall length, sets the symmetry of the molecule. That's all you need to know about a diblock copolymer in order to do the statistical mechanics and calculate the familiar states of self-assembly which occur on a length scale of nanometers, tens of nanometers, the length scale being governed by the size of the polymer molecule. So here I summarize the theoretical self-consistent field theory phase diagram. I'm going to use the combination theory parameter chi times n, but all you need to know is that this is proportional to 1 over temperature. So if I heat the material up or go to small values of chi n, it disorders. And if I cool the material, it takes on ordered states that are determined by the composition of the molecule. The familiar phases that are known in diblocks are spheres, cylinders, a network, lamellae, and then the inverted phases. And experiments have shown that there's very close agreement between the geometry of these states and the theory that predicts them, and even close to quantitative detail. Today I'm going to focus on just the simplest of these self-assembled states, the spherical or seemingly spherical micelles. And if I'm to draw a picture of what that geometric object is assumed to look like, it looks like a micelle. The ones I'll talk about have about 200 chains per particle, and the whole talk is going to focus on this class of self-assembled materials. So I'm going to jump right into a phase portrait in these theoretical chi times n units, remembering again this is like 1 over temperature, as a function of the composition, that is how much of the polylactide versus the length of the polyisoprene is in the molecule. The chemical details are not particularly important here, but we actually synthesized a lot of these compounds. In fact, Tim Gillard, who just graduated, made a lot of compounds and categorized this corner of the phase diagram, which I'm going to show you has BCC packing symmetry, hexagonal packing symmetry, and then he discovered, along with Sang-Woo Lee, a region that had not been anticipated in the past using theory. And that's this Frank-Caspar sigma phase, which I'm going to describe in some detail. I'm going to start by focusing on a single sample, a sample that has an ordered-disordered transition temperature. That is a melting temperature from self-assembled micelles that are liquid-like or disordered. That's at low values of chi n or high temperature. You cool it, it makes body-centered cubic, and I'm going to show you when you cool it further, it makes this Frank-Caspar sigma phase. We're going to use a standard technique in material science to understand the evolution of the structure when you cool it from the disordered state as a function of time. This is what's known as a time-temperature transformation diagram in metallurgy. I'm going to take the disordered liquid and I'm going to quench it rapidly relative to the time it takes to nucleate and grow the ordered phase. In this case, it's going to be a body-centered cubic phase. This envelope of times governed by nucleation limitations just below the ordered disorder or melting temperature, and governed by diffusion limitations when quenched deeper, lead to a fastest rate of nucleation of this phase, which is about 15 minutes, which means we can quench the sample and then study it as a function of time. And in 2010, Sang-Woo Lee discovered that he could follow the evolution of small-angle X-ray scattering diffraction, which you'll see here, over a period of about 15 to 20 minutes, evolves to have a descriptive number of Bragg peaks with a set of indices which define it as a body-centered cubic lattice. And what I've shown is a depiction of the unit cell, the quote-unquote spheres, and pretty soon I'm not going to call them spheres because they can't be spheres. And the size of these particles, the core, are about 41 angstroms, or 4.1 nanometers. And importantly, they have about 200 of these polymer chains per micelle. Sang-Woo did another experiment. He took the same system, he quenched it deeper, and he waited a long time. And what we discovered is that this classical nucleation and growth envelope was disrupted by an event that occurred quicker, and then something else happened that long time. And I can show that using the X-ray scattering patterns acquired at the synchrotron source at the Argonne National Laboratory, where these experiments were done. What he discovered is when he first quenches the sample, there's a very broad peak, which is symptomatic of the disordered arrangements of micelles that are self-assembled, but in a liquid-like state. And then with time, we see a diffraction pattern emerge, and over a period of about a dozen days, this development of a rather complicated, densely packed set of diffraction peaks emerged. And this was something that had never been seen in a block copolymer before. You remember the body-centered cubic state, that's the one that was predicted or anticipated by self-consistent field theory, and people had reported that for the last 30 years. So this came as a shock that something this complicated had emerged. In fact, when Sang-Woo showed me this result, I pushed him out of the office. I said, that's obviously an artifact. Nobody's ever seen a pattern like this. To his credit, he came back, and he came back again. And he convinced me, based on results that emerged from a Rietveld analysis, that this diffraction pattern, when corrected for background scattering and looked at in the vicinity of the dense array of peaks, could be very closely approximated by a crystal structure which was truly interesting but complex. It turns out it has tetragonal symmetry, a P4 sub 2 M&M space group if you're into crystallography, but the key point is it had 30 particles per lattice site. This crystal structure was an immense unit cell. Remember, each particle has about 200 chains, and there are 30 of these particles per unit cell. So there are millions of atoms per unit cell, and as I've said, nobody had seen this before. It took us about 3 months to figure out what this was. This was the first unit cell and molecular structure that Sang-Woo put together. We don't have a lot of money in Minnesota, and this was actually, all kidding aside, if you've ever tried to make molecular models, it turns out marshmallows and coffee Twizzlers, both cheap and effective, my kind of molecular model. Sang-Woo put this together and brought it to me. And I've done a better job, and we'll show you there's a more rational way to look at it than this, but this is Sang-Woo Lee not long after he brought me this model. So what is this curious phase? This phase turns out to be what's called the Frank-Caspar phase. Turns out to be very familiar to people in metallurgy. If you weld steel, if you get a bad weld, a brittle weld, that brittle weld is probably the Frank-Caspar sigma phase. It occurs in uranium, and it occurs in many other alloys. So there was a clue that there was some connection to what happens in metallurgy. We were able to take electron microscopy images using stained samples from a related but different polymer. And those images, although slightly twisted and skewed, reinforce the top-down view of what the tiling elements for this complicated phase were. And if you look at the little image that's shown in here, this tiling of spheres projected down the C-axis of the unit cell is trying to acquire something with aperiodic order. And that's the reason this is called the quasicrystal approximant. Essentially, every quasicrystal, mostly discovered in metals and alloys, only recently in soft materials, has an underlying translationally periodic crystal structure, and the quasicrystal, as I will show, is the aperiodic approximant. So we knew at this point we had something unusual and quite interesting, and we knew that based on the long-term X-ray scattering and related rheological measurements, what we had was a series of phases that were disordered-like at high temperature, body-centered cubic-like near the melting point, and then at the lower temperature was this complex 30 particle per lattice site, 30 particle per unit cell structure. I'm going to introduce a concept that evolved after we had characterized this material and were attempting to rationalize why a self-assembled soft material might decide to make such a complex phase. And the concept that's most important is well established in soft matter, especially in block copolymers. In order to fill space with this single component system, although we have 20 block polymers per micelle, we actually have a single component system, one kind of molecule that then self-assembles, and then those self-assembled particles pack space. They're soft materials. They are governed by the desire not to leave any voids. The density or packing of the segments, the repeat units, at the repeat unit scale, half a nanometer, is governed by van der Waals interactions, and it fills space at constant density. And if that's true, then the particles cannot be spherical. You can't have three-dimensional order imposed on an ensemble of particles that fill space at uniform density and not have voids if they're not spherical. So we knew that there was a concept that was going to have to be satisfied, and the way I've drawn this is to show you what our particle actually has to look like if it packs on a body-centered cubic lattice. It has to take on the shape of a truncated octahedron. That's simply unavoidable. If we were packing ping pong balls, we could have void space. But this soft, pliable, soft material is not going to leave void spaces, and so it deforms into this kind of truncated particle. On the inside is the core, the polylactide. On the outside is the corona. Here I've sketched the density profile of the red, for example, as a function of radial distance in the particle. If I put those particles together in the unit cell, they have to fill space this way. So the core is trying to be spherical, but the particle as a whole has to adopt the lattice symmetry associated with the space filling. And my daughter turns out to be a photographer, an artist, and I challenged her. It's kind of fun. She's not a scientist. I challenged her to produce an image that would convey this idea. And she came up with this. If you take balloons and you put a force on the balloons and you fill space, they squeeze out the space and they assume the symmetry of the lattice. And this is precisely what goes on where the van der Waals interactions pull the particles together to fill space. So what we have then in the BCC case is a unit cell made up of these very single type of polyhedra. When we go to the Frank-Caspar phase, by solving the crystallography and knowing the composition, it turns out there are 5 different Wyckoff positions, 5 different crystallographic sites in the crystal structure. that are populated, by definition, by 5 different polyhedra. What I've done is explode the unit cell into the 5 different types of polyhedra that are defined by the positions in the crystallographic solution to this problem. And if you remember what the diffraction pattern looked like, we had 48 reflections. We had lots of information to go back and solve this diffraction problem. And so if we blow this up in a more illuminating way, what I show you here are the 5 different polyhedra that unavoidably will tile space in order for these soft particles to fill space. And I've shown them here based on the precise shapes that are required based on the solution to the crystallographic problem. What I've also shown is the occupancy number. There are 2 of these, 4 of these, 8 of these, 8 of these, and 8 of these. And another interesting fact is that they have different volumes. In order to tile space with these polyhedra, and remember again an important point, that the block copolymer is a single component molecule, and so every block has the same composition. Every micelle has to have the same amount of core and corona, and that simply unavoidably leads to polyhedra that vary in volume between 91 and 106% of the mean value that's shown most precisely by the one in the middle. So we have 5 types of polyhedra. They're non-spherical, and they have different volumes. This concept is then going to lead us to the concept that I call sphericity. If we look at this picture that I drew before, near the disordering transition, where the thermodynamic competition between the red and the blue blocks that force them to microphase separate gets weaker, we have a sort of fuzzy interface and an imposition of this polyhedron shape on the core. But when we cool the sample down and the blocks segregate more strongly and the composition profile becomes sharp, we're imposing a stronger and stronger interfacial tension. That interfacial tension is pushing the core to be spherical in order to minimize its net integrated interfacial tension on the overall free energy of the system. And what that creates is a competition between the lattice symmetry, which is imposing this tetragonal symmetry, imposing polyhedra shape, and the preferred spherical shape that the micelle would assume if it were an isolated particle floating in a sea of unrestricted space. So there's this competition that's created. And I want to explain this concept of sphericity using the Platonic solids. If I draw the Platonic solids from the tetrahedron all the way up to the sphere, we know based on a notation interested by the mathematician Polya that we can identify something called the isoperimetric quotient. That's just the ratio of the volume squared over the surface area cubed. This is a dimensionless parameter. It's been normalized by 36 pi such that this isoperimetric quotient is 1 for a sphere. As I go down the Platonic solids, the isoperimetric quotient goes down. In other words, the most spherical particle has an isoperimetric quotient of 1, and the least spherical particle, in this case the tetrahedron, has 0.302. You all know that the only particle in here that can tile space in 3 dimensions without any voids is the cube. The other ones can't fit. The only way they can fill space without voids is to deform. And what happens in these soft materials is they assume polyhedra that can fill space in 3 dimensions without voids. Face-centered cubic can do it. Body-centered cubic can do it. These are the sphericity factors, or the isoperimetric quotients. And if I ensemble average the polyhedra that we've determined for our system, this Frank-Caspar phase has an average sphericity which is higher than the body-centered cubic. So as I cool the sample, and I have this driving force in the ground state to become spherical, the system reorganizes itself into a set of particle shapes that allow it to fill space with periodic symmetry, but in a form that is closer to being spherical. This is the key concept in this entire talk. Sphericity favors low symmetry phases. I want to go back and reinforce this. We have BCC becoming Frank-Caspar sigma. We have 30 particles breaking up into 30 particles with 5 different polyhedra and the occupancies I've indicated. So here's the stoichiometry. And when that happens, they also break up into particles that have different volumes. The only way for this to happen is if there's mass exchange. Mass exchange. Some of the particles shed some of the block polymer, and other ones pick it up. This is an important ingredient in what I'm telling you today, that there has to be mass exchange for this transition to occur. But it's favored, we believe, thermodynamically because of the tendency for these particles in the ground state to become more spherical. We can test that idea doing an experiment. This is the X-ray scattering that I showed you before. You quench the disordered state down into the region where it makes BCC. You quench it to 25, it makes Frank-Caspar sigma. In order to go from BCC to Frank-Caspar sigma, in fact, in order to go from disorder to BCC, there has to be mass exchange. A disordered state has an infinite number of disorganized polyhedra with a continuous distribution of sizes and shapes. That's reflected in this disordered scattering pattern. When it breaks symmetry, there has to be mass exchange. And that led to an idea that we could take these self-assembled particles, and if we looked at the differential scanning calorimetry trace, what we identified is that the core of these particles has a glass transition temperature of 5 degrees centigrade. That's what this DSC trace indicates. That means if we go to 0 degrees centigrade, the core will be glassy, frozen, but the corona is still fluid and liquid-like. So then we have particles that cannot have mass exchange because we've arrested the mass exchange by freezing the core. You notice the glass transition temperature of the corona is minus 66. So we make frozen fuzzy balls. And if we go back and quench the sample to 0 degrees and wait a day and then wait 48 days, the system doesn't order. It can't order because it can't exchange mass. We've trapped the particles in a distribution of particle sizes. This is actually a very interesting state of matter. It's what I would call a soft glass, and that's another area we do work on now. But I'd like to point out, if we grow this phase and then cool it, we've locked in this distribution of particle sizes. They stay, and in a result that I'm not going to have time to talk about, curiously, if we quench the BCC state, it actually melts. And I don't have time to talk about that, but I will tell you, I lost $5 to Sang-Woo Lee over this result. Okay, I'm going to summarize what I've told you. In soft materials, and I'm going to argue this applies to block polymers, lipids, surfactants, dendrimers, and other self-assembled, what we call mesomorphic materials. We start with molecules, they self-assemble and make particles. They have uniform density. This is the controlling field, the self-consistent controlled uniform density, and the dynamics are controlled by mass exchange. What I want to talk about next is what we think happens in metals and alloys. If we go to the periodic table, thank you, Martin, you're still taking care of me. I got a little problem here. Thank you. If we go to metals and alloys, and I pulled this out of Cattell's book in solid-state physics, what we know is that the vast majority of the periodic table contains metals. Most of them are body-centered cubic, face-centered cubic, and HCP. But there are some which are listed as complex, especially down here in the actinides and lanthanides. The one I'm going to focus on in a little bit is going to be manganese. Manganese actually makes fascinating complex phases. And then, of course, if we start blending the metals, we get alloys, and I'm going to focus on copper and zinc and copper and cadmium. They make extraordinary complex phases. We can see this in the classical phase diagram for copper and zinc as a function of melting temperature. These alpha, beta, gamma, epsilon, delta, these are single phases of mixed copper and zinc. This is how brass is made, right? This has been known since antiquity. And if you go into this diagram, these are FCC, BCC, and then something that's listed as complex cubic. I'm going to show you what that is in a minute. This is what that complex cubic is. It's copper 5, zinc 8, close to that stoichiometry. The cluster that goes into the unit cell has 26 atoms in it. This is a complex array, and this is something that's known as a Frank-Caspar phase. Very analogous to what I've talked about. I want to look at the analogies electronically between zinc and copper. So what I've done is taken the FCC copper and drawn the 111, the close packed hexagonal plane, and I've done the same thing for what is now the 100 plane, because zinc is hexagonally close packed and copper is FCC, face-centered cubic. Both of these have a common close packed plane, and if I look at the way the electronic properties are governed, for example, in FCC, the metal, what I have is one electron that gets donated to a conduction band. I take those electrons from all the atoms, of course I fill up a conduction band up to the Fermi energy, right? The Fermi energy is half the height of the conduction band. It's a half-filled band, the classical metal. And if I look in reciprocal space, and what I'm going to say about the metals is going to be reciprocal space as opposed to real space for the block polymers, I'll connect those later, what we find is that if you put the first Brillouin zone in, that the sphere, which represents the Fermi sphere, the Fermi surface, in a classical free electron model, that classical free electron model defines a half-filled conduction band, which is spherical and contained in the first Brillouin zone of this FCC metal. For the HCP, it's slightly more complicated. You need both the first and the second Brillouin zones, which together make what's known as the Jones zone. And this is the polyhedra that actually encloses the Fermi surface, the half-filled band in the case of HCP. You can go to Jones theory, which was developed in 1934, and understand what happens when you take copper and start adding FCC zinc atoms to it. At the low composition range, the atoms go in randomly. It makes what's known as a virtual crystal. The atom goes in, but the zinc has 2 electrons per conduction state. So it starts contributing additional electrons to the conduction band, but it still has the same crystal structure. It still has the same Brillouin zone. But what happens? Those electrons go in, they start filling out the conduction band. The Fermi volume, the surface, increases in size. The volume of the conduction electron band grows out to the point where it touches the first Brillouin zone. If you want to put any more electrons in, you have to open up a band gap. That costs energy. So what happens? Mott and Jones in particular, in 1934, developed this electron counting theory for how you understand conductivity and structure in these alloys. What happens is the system changes lattice symmetry. It goes BCC, and then it goes complex in order to become more spherical and afford a little more volume to accommodate these conduction electrons. You see, I'm introducing the sphericity argument now, but I'm introducing it in band theory associated with alloys in reciprocal space instead of polyhedra filling soft particles in real space. So this Jones-Mott theory is incredibly predictive. When this particle filling polyhedra was developed for the polymer side. My colleague Chris Layton one night looked at me, he said, "Oh my gosh, that's Jones theory. Go read this book." And it destroyed the next 3 weeks of my life. I had to learn quantum mechanics. If you use this theory, you can actually almost quantitatively anticipate where these phases develop. And what's really extraordinary is the complex phases reflect the ultimate tendency for the Fermi surface to be as spherical as possible and fit into one of these complex Brillouin or Jones zones. I want to show you another example, a beautiful example taken from copper and cadmium. Again, FCC and HCP. This is the phase diagram. Stephen Lee from Cornell in 2013 wrote an astonishing paper where he did the full proper band theory calculation for what the structure of these alloys should be. I'm going to focus on this one. It turns out in 1967 at Caltech, Sten Sampson figured out the crystal structure of cadmium-3 copper-4. Turns out it has 1,124 atoms per unit cell with a gigantic lattice parameter and 29 Wyckoff positions. That's 29 different types of polyhedra by analogy with what I'm talking about in the polymer case. You'll also notice that buried in the middle of the 110 plane is a 5-fold symmetric element. This sample is trying to make a quasicrystal, and it needs to cobble out a unit cell that's gigantic in order to embed that 5-fold symmetry inside the crystal. So this is the result that Stephen Lee calculated for the Jones zone for this particular alloy. It turns out it has 68 faces. This polyhedra in reciprocal space is very close to being spherical. And what happens, as I said, is that the free electron sphere is nearly spherical, and it induces a low symmetry phase. Turns out it's a Frank-Caspar phase in order to accommodate that electronic structure, band structure, when it's embedded in three-dimensional reciprocal space. And I'll point out that the diffraction pattern that we had for the Frank-Caspar phase in the block polymer, those are all higher order Miller index planes because we have basically the same thing happening. We have this complex low symmetry crystal which is accommodating the polyhedra. Okay, so what I started out is I told you about molecules that self-assemble that occur as polyhedra in real space and can be described, it turns out, by strictly statistical, mechanical, classical theory. The metals have electrons that are part of atoms. The governing field is not constant density, it's constant charge. And the mechanism of competition is through spin-dependent charge exchange. It's governed by quantum mechanics, and it's governed in reciprocal space. And I'm going to argue that there's a common theme. The common theme is what we call sphericity. I believe there's a geometric underpinning to the formation of quasicrystals and quasicrystal approximants. Okay, enough solid-state physics. I come back to the polymer case. Now we know we have a quasicrystal approximant. We should be able to find the quasicrystal. And what we've done in the last year or so is to take another sample, to design it to have a slightly higher order-disorder transition temperature. I'm going to go fast here. It has the same equilibrium diagram that I showed before, and we've worked out the complete time-temperature transformation diagram for this material, except we've now elevated the melting temperature by 20 degrees. We've speeded the system up so we could go deep into the soft glass regime and still have time, upwards of half a year, to see the way the quasicrystal, I'm going to show you, and the sigma phase evolve. So what I'm going to do is take an analogy again with metal alloys. This is exactly what people who study metal alloys do. I just took this one from the literature. If you quench a metal fast enough, you can supercool the liquid. If you quench it deep enough, you can make a glass, a metallic glass. If you wait at a deep point, you can go out and actually grow the crystalline phase. We're doing exactly the same thing with these self-assembled soft particles. So I'm going to take the sample, quench it. That only takes about 5 seconds on the synchrotron, and then watch with time and see the way the sigma phase evolves. Here's the X-ray scattering patterns we took about a year ago. You notice we get the sigma phase after about 2 days. We start disorder, but something different occurs in between. What that is, I'm going to tell you, is a quasicrystal. In order to expand the time frame over which the quasicrystal survives, we just quench 10 degrees down deeper in temperature. We have to wait longer, but this window of blue, the quasicrystal, now occurs over a period of about a half a year. So we start out disordered. We now have changed the diffusion coefficient, the mass transfer coefficient, and remember, mass transfer is required to break symmetry. We've made that go slower by quenching deeper, and we can study in detail the evolution of this quasicrystal. How do we know it's a quasicrystal? I'm going to cut to the chase on this, show you a comparison with the first soft matter quasicrystal that was ever discovered with a dendrimer. This was done by Zhang and Unger and co-workers, reported 12 years ago. There's their powder pattern. They actually had fibers and the analog of single crystal diffraction. Here's our powder pattern. And this is what the tiling sequence would look like for the down the axis, the C-axis of this two-dimensional quasicrystal. This has aperiodic or rotational symmetry, but no translational symmetry. Well, now that we know how to grow these phases, and we can now manipulate them, for example, I can grow that phase, heat it back up, and see how it goes from the quasicrystal. How does it evolve towards equilibrium? And this is a result that, again, for us was very illuminating. We grow the quasicrystal, we heat it up to 50 degrees, and now we speed up the kinetics, and we can actually watch the evolution of the sigma phase. And you'll notice that the 002 reflection, that's the C-axis, 002 reflection for the Frank-Caspar sigma phase, is precisely the one-dimensional periodic order that then has two-dimensional aperiodic order, which I've depicted here. So the quasicrystal becomes a crystal by retiling the two-dimensional order. And we're able to experimentally investigate that in exquisite detail. This is something of a summary slide. I can supercool these liquids and control the time frame of nucleation and growth by adjusting the order-disorder transition temperature. I tune that with the molecular weight of the block polymer. I'm able then to change the dynamics where it's fast chain exchange up near the melting point and slow chain exchange, which means I go from a state of ergodicity. The system is equilibrating up here rapidly, but when I quench deep, I create a state of particles that can exchange change, but they're soft and they can jiggle around. This is actually a soft glass, but it's a very special kind of soft glass. It's trapped in a state where it can't order because it can't redistribute the volumes and sizes of the particles. I believe this is a key underpinning of the way soft matter breaks symmetry, and I believe it gives us clues as to why quasicrystals form in general. And what you'll note is that the quasicrystals in this case are not equilibrium. These are non-equilibrium transient states that emerge from this supercooled glassy state. Very interesting. This is an area that we're continuing to work on. We've just published this result a couple of months ago. So I come back to the pattern I showed to start with. The people that think about quasicrystals tend to think about atoms with different sizes, that they fit together like particles with different sizes, the way Penrose put together his two-dimensional tiling pattern. It's geometric. I believe This is not the mechanism. The mechanism is the sphericity argument. It's geometric, but it's geometric in a completely different way because these particles are springing from a state of disorder where there's no symmetry associated with the particles. There's no particle shape or size that governs the formation of these quasicrystals. They're not puzzle pieces. They spring and develop because they're driven to go to this spherical symmetry when you get down to the ground state. But as I point out, the quasicrystals in our case are transient and non-equilibrium. So I come back to this question. I've made an analogy with what happens in metals, and I don't know if this is true, but the work of Lee from Cornell suggests that the underpinnings, the reason quasicrystals form, may be this geometric sphericity argument. Are they equilibrium or non-equilibrium in the solid state case? I think the jury's out on that. The fact that you can grow a big single crystal does not mean it's an equilibrium state. In the soft materials, we've made the case that what we have are non-equilibrium particles. But I think, as I've said, the jury's out. So I'm going to leave you with a perspective. I'm a polymer guy and was fortunate to have stumbled into this problem. The beauty of the Diblock copolymers and other multi-blocks is they're one-component systems. There's no getting away with arguing they have different internal symmetry. They're all the same. I can tune the composition. I will tell you, we have 3 other Frank-Caspar phases now in Diblock copolymers. I can tune the free energy scale by adjusting the degree of polymerization and the strength of the interactions. That's the chi parameter. I have mesomorphic particles. They're many-chain particles, and that's a key ingredient. And they can exchange mass in order to split the particle dimensions according to the desire to satisfy the sphericity condition. And very important, there's a decoupled length scale. The constant density is driven by monomer scale packing with van der Waals interactions. That's the glue that holds the material at uniform density. The order forms at the radius of gyration scale. That's 10 or 100 times larger length scale than is occurring when you go to the condition that keeps the density constant. And that's in some ways analogous in reciprocal space to taking electrons and throwing them into the entire band gap, which fills up, of course, the whole sample. So there's this, I think, lovely analogy between real space and reciprocal space with obvious differences. And as I said, in the polymer case, we can use classical statistical mechanical tools, and we're not trapped by the dilemma of trying to do proper band theory calculations and density functional theory where everything's happening at the angstrom length scale, which is very difficult to decipher. If you want to know more, you can look at this article. We've also talked about manganese. It turns out manganese has BCC, FCC, beta, and gamma. This phase has 58 atoms per unit cell, including 4 different crystallographic sites that are magnetically active. And we believe understanding these complex phases is related to the same arguments that I've made for the alloys. And I'm going to finish with that and open up for questions. Thank you.
Some of us love reciprocal space, but this is actually the first time that I've had somebody making geometrical comparisons between real space and reciprocal space. Now, questions? And we need the microphone.
I'm very much intrigued about the time scales. It's very fortunate this after quenching it, because sometimes it's minutes or days. It's very convenient to measure. Is there any way to predict when it's in milliseconds or when it's in years?
Qualitatively, yes, we can predict based on the molecular weight of the polymer, and if we measure the rheological properties which give us the time frame. In the disordered state, there's a time constant for the micelles to move around. Once we know that, we can anticipate how deep to quench in order to stretch out the time scale. But much like glasses, quantitatively predicting what that time scale is not something we can do yet. But qualitatively, we can design, and that's what we've done. We've designed the polymer. In the second case, to find the quasicrystal, we designed it to be faster than before, but slow enough that we could still quench it and bypass nucleation and growth. So qualitatively, we can predict that. Yeah.
You heard about the constant density you talked about. What if we have quenched the sample and there is no way it can reorganize? It still doesn't try to fill out the gaps by changing the density in these local places? So.
Yeah. So in the disordered liquid state, it's micelles that are packed at uniform density. We quench. It's still micelles packed at uniform density. Density is a little bit higher, you know, fraction of a %. But in order to do anything, either the particles can, they're still soft, they can wiggle around, but in order to change the distribution of sizes, they have to exchange mass. And this decoupling between the density being constant, that's a field, right? That's a field that holds the system. That decoupling is what makes the system so tractable.
And you have spheres in BCC transforming into the Frank-Caspar phases.
So I'm going to correct you now. Now you've learned they're not spheres, they're polyhedra.
Oh, sorry. You've got some kind of balloon-shaped object.
Truncated
But
icosahedra.
but
I
in
mean,
the-
yeah, okay.
Yeah, but in the BCC structure,
Yeah,
they're all the same.
they're all the same. There's only one lattice site
Yes.
per unit. There's only one particle type per unit
Yes.
cell.
So I just want to understand, when it actually has to go into the Frank-Caspar
Yep.
phases, it has to rip out a molecule from the balls
Yeah. Yep.
and to move over in order
Yep.
to make different kind of balls.
Right.
Or whatever you
Right.
call them.
Exactly.
Now, isn't that a tremendous enthalpy price to pay? Because all of a sudden you have this block that has to transfer between all the majority blocks
Sure.
of the different kind. It must
any-
be a nightmare to do that journey.
It was obviously not a nightmare because it happens. There's an activation barrier that's set by the very term you're giving. It takes an increase locally to fluctuate out a critical nucleus. It has to rise beyond the critical nucleus free energy, but then once it starts and goes far enough, it's downhill, that's a nucleus, and then it can grow. I'm going to argue it's exactly the same principles that govern nucleation and growth in any phase transition. And of course, there's a free energy price to pay, but the system is fluctuating, so it can do that.
And if we could look at the shape of just one polymer molecule, one block copolymer molecule, maybe the minority phase will coil up and really try to reduce its interface in the majority phase.
And that's a perceptive point. What is the molecule actually doing when it goes out, moves, and gets caught? What is it? I don't know. That's where we need the theory.
How could we look at the molecule, Frank?
To look at its conformation?
Yes.
I don't know, because the concentration of those molecules that are flying around is necessarily going to be very low.
Here the correct answer would have been deuteration and neutrons.
No, you still can't. No. We can deuterate, but remember the number of those molecules that are flying around, the fraction of the molecules that are flying around is going to be very low. And so you have to wait for many of them to do that. And so seeing one of those with neutron scattering embedded in this mesoscopic structured material, I don't see how that could work.
A strong neutron source.
No, even then, you're going to have you're trying to find the signal in a noise.
We like challenges, right? So that would be interesting.
Well, I'll tell you what, I agree with you. I need a lot of beam time in your new European spallation synchrotron,
all right.
the neutron.
Now we're talking.
Yeah.
Any more questions? One more over here.
No, I didn't want to.
Record it, so.
So can I, well, thank you for a beautiful lecture. Can I think about the transition from a quasicrystal to the final Caspar, what were they called?
Frank-Caspar sigma phase, yeah.
So with the tetrahedral structure, can I think of that as a kind of two-dimensional to three-dimensional thing? I mean, the quasicrystals, are they sort of two-dimensional, so layered-like structures?
Yep. Yeah,
Okay.
that's you can think of the quasicrystal state as one-dimensional periodic order and two-dimensional aperiodic order. And then when it transforms to the sigma phase, it becomes three-dimensional periodic order. And that's a fundamentally interesting transition. And it goes back to what we talked about at lunch. Just this year, the Nobel Prize in Physics for hexatic-related and under two-dimensional phenomena. I think there are some very nice analogies that may be fleshed out with that transition.
But how can I think about sort of a movie of what happens when I go more quickly into the quasicrystal phase.
Yeah.
And then there are some final rearrangements.
Yeah.
What do they consist of?
Yeah. Here's my speculation is that the quasicrystal picture I drew with the tiling was the idealized tiling, which has something called inflation, that it has some kind of self-similarity out to infinite distance. If you think about it, the unit cell for a quasicrystal is actually infinitely large. I don't think that's quite what we have. I think it breaks symmetry locally. They can ratchet and tile, but they don't tile with the perfect inflation rules. They tile locally, which still brings you angular aperiodicity, but the actual correlation length is probably short range. And because of the diffusion limitation, much like the glass transition, I believe those are local non-ergodic events that allow the system to go on the way and gain enough free energy locally to head towards what is the equilibrium state, which is then the full three-dimensional order. The unit cell for the Frank-Caspar phase is gigantic. To get a nucleus of that system probably requires hundreds and hundreds of particles. That's billions of molecules. So this is an intermediate state. Whether or not the supercooled glass is thermodynamically unstable or whether it's simply a pathway and a free energy surface that's preferred, now we get into the details. If this is answering your question.
We're now having a reception outside in a few seconds. We agreed with Frank that if anybody didn't ask a question but still has something to discuss, we can spend another 5 or 10 minutes before Frank also will join the reception. But that is the case. There is another question, but you can't say it now. You want to do it now? Everybody's waiting for reception.
Yeah.
It's okay. It's okay. If it's short, is it short? Bring it on.
Get the mic.
I'll be brief. So I was really fascinated by how you drew the connection between metallic systems and polymer systems.
Yeah.
But I can't help but wonder if maybe there are other analogs in other types of system that maybe you've thought about. Or
Yeah, and that's a great question. And I think the analogs in soft materials are clear. Surfactants, lipids, other mesomorphic systems. And in fact, my colleague, Mahesh Mahantapa, who's in my department, has just discovered the same sequence of phases, BCC, sigma, and related Frank-Caspar phases in low molecular weight surfactants, which have water and a surfactant and counterions. So I think any system that's, as I say, mesomorphic in the soft material category. Mesomorphic means particles that are self-assembled and make larger geometric objects. I think we'll have analogies.
So I've spent some time looking at relaxer dielectrics, and they have an ergodic, non-ergodic transition.
Yeah.
And in a number of occasions, if I cool them too fast, I see these extra peaks from some long-range structure.
Yeah.
And I say, okay, I can't explain them. I can't fit them with my read
Yeah.
field refinement. Obviously,
Yeah.
I quenched the sample wrong.
Yeah.
And then we go through and we cool it much slower, and then
Yeah.
the data makes sense, right?
Yeah.
I mean, it sounds like exactly the same
Yeah.
kind of thing, except with charge disorder rather
Yeah.
than a geometrical transition.
Yeah, and you notice I leaned on the soft material side. I want to bring my colleague Chris Layton back in. He's taught me a lot of quantum mechanics, and I understand in the system I've discussed, I'll bet there are many other analogies.
Spin glasses, right?
Spin glasses, I agree. I would love to flesh those out. I'm not qualified to make intelligent comments about that, but I love the idea that there may be a connection there. I mean, that's what sort of drives me here, finding those connections. Thank you.